Hello, this is exercise 7i. This is goodness of fit tests. I should make sure you are aware these are sometimes called GOF tests, but we've seen these before. Now, if you haven't seen these videos, I'm hoping you have, but it's 6C.1, which was year 12 work really, and also exercise 6C.2. I think we did a few more in that. So have a look at those videos and make sure you know what's going on in them. I suppose a little reminder won't go amiss though. So if you recall, we basically have a model which is suggested to us. It might be the binomial distribution is appropriate. It might be we've got this idea that the probabilities of all these events are all the same, or it might be it's the geometric distribution which is appropriate. But one way or the other, they suggest a model, and it's our job to see if there's enough evidence to say that this model doesn't seem to fit. And we do that by finding chi-squared, and it's a chi-squared GOF test, as I've already explained. And if you remember, you have some observed data, and you compare that to the expected data, or the expected frequencies that you would get using the model. And if it's a big enough difference, then this statistic is big, and that means chi-squared is big. And if it's too big, then we accept the alternative hypothesis, H1, or rather we reject H0 is a better way of describing it. I should remind you that although we had that formula there, this sigma O minus E all squared over E, a much better way of finding it is using the calculator. And you can find chi-squared GOF statistic using the calculator by pressing stat. Now stat is here on the calculator, obviously, using the edit function, going into L1 and L2, and then entering the observed data and the expected data. We'll have a look at that in a bit. And once you've done that, you can go back to it and press stat again, press test, chi-squared GOF test, and calculate, and it gives you the chi-squared value. Now, on the face of it, that's enough. But you need to make sure you also get out of the calculator the chi-squared expected values. So if you don't get the expected values, you'll be in trouble. A reminder also about degrees of freedom. Degrees of freedom basically comes back to this way we then measure whether a chi-squared is big enough. Now we use the critical value tables to determine that, but we need to know the number of degrees of freedom so that we can get the right critical value. Now, say I had a situation from, I think this was in exercise 6C.1. We might have just had some categories, and we might have had so many red things happen, so many blue, so many green. So I've got 3 categories. Now in this situation, I would say that although there's 3, I always have to take away 1 because of the number of categories. I think you think of it as totals. So for instance, say I was expecting this to be 10 things, and this was 10, and I was doing it. I'm going to say I'm doing it 30 times. So I'm expecting all these things to be equally likely. Can you see how this answer here? I've got no choice. This is, well, that's 10. That's 10. That's 30 in total. So this has got to be 10. I had 1 less choice, if you like, in determining how many I expect to happen. And so for that reason, I've only got 2 degrees of freedom. And in these situations, then you always do n-1, where the 1 is because of the n categories. Binomial questions are slightly different. You usually get you usually say that binomial n comma p. So already I'm thinking, if I'm having to estimate p as well as I've got this problem with the totals, I therefore do n-2. Notice, by the way, if I know for certain what p is, now, for instance, if I was to roll the dice and I knew exactly what p is, then I wouldn't need to take away 1. It would only be n-1. But when I'm estimating p, then it's n-2. Poisson distribution questions, very similar. Usually as a lambda, an average number of things that happen, it might be telephone calls to a telephone line exchange within a 10-minute period. It might be I know exactly what lambda is, but likelihood is I don't. I would estimate lambda to be, I don't know, 2 calls per minute or so. And there, for that reason, I've got n minus 2. One for the totals, and one for the fact that I've estimated lambda. Normal distribution. Now, look, sometimes in normal distributions, they say you know mu, you know sigma squared. So in that case, notice what I'm writing, n minus 1, because these don't count as being, if you like, restrictions on my degrees of freedom. So my degrees of freedom is just n minus 1. The 1 for the n, if you like, I know the number of categories. And if I don't know that, if it's a mu comma sigma squared, both estimated, then don't be surprised it's n minus 3. One for the totals, one for the mu, one for the sigma squared. I suppose the key thing here is if you know or don't know the values of your parameters. Now, bearing all that in mind then, PDFs are what we're looking at today. And we are going to use a GOF test to determine whether a suggested PDF is consistent with the data that we've got. We'll need to know the degrees of freedom, and these are also n minus 1. The number of intervals minus 1. It's very similar to the number of categories we saw before. And notice also we're going to have to be able to find this f of x, probability from the f of x rather. And we do that by integration. So in order to find the probability, we will need to integrate, and once we know the probability, we can times by n to get the expected values. So I've just realized that says the wrong thing. That should say the expected values. Okay, so here's my example. The length of time in minutes that a customer has to wait at the Tilden shop is thought to have a PDF of a half sine x between 0 and pi. The manager samples 40 customers. That's important. We'll need that in a bit. But first of all, I suppose I want to highlight the fact that with these, and obviously they've split them into 4 categories, 4 intervals, and they've told me how many customers waited these times. These are the observed data. So it's been observed that 7 customers waited between 0 and pi by 4 seconds, or minutes. What is it? Does it say? Well, it's minutes. I therefore need to work out the expected number. And in order to do that, I'm first of all going to have to work out the probabilities. So let's concentrate on this one first. That's from 0 to pi by 4. So this probability is the integral from 0 to pi by 4 of the function, which is a half sine x, dx. Now, when I integrate half sine x, I get minus a half cos x. So I need to substitute those values in. What was it? 0 and pi by 4. And there's nothing stopping me doing this as a decimal, actually, because I'm going to need to do it. I'll do it exactly. When I put these numbers in, pi by 4 of cos gave me minus root 2. It's a half of it, remember, so minus root 2 over 4. And then I take away, I put 0 in, cos of 0 is 1, so it's minus and minus a half. And when I did that, I got 2 minus root 2 over 4. You can check that on your calculator. And as a decimal, that is 0.1464. So check that on your calculator and make sure you agree with my maths. Notice that means I can now work out my expected number. And I can do that. Once you get a probability, you just times it by the n. So in this case, I times by 40. And doing that, I get, again, check it on your calculator, 5.856. Now I'm going to do another one. And the next probability I have to do is for the second interval. And that goes from pi by 4 to pi by 2. So a lot of this is repeated work. I don't need to do it all again. It's just minus cos of x between now, well, pi by 4 is at the bottom, pi by 2 is at the top. So if I put pi by 2 in, cos of pi by 2 is 0, so that's easy, minus, and if I put pi by 4 in, I get actually out what I got in last time. Last time I got minus root 2 over 4. So obviously minus and minus gives me root 2 over 4. And root 2 over 4 I got 0.3536. Now don't forget, it's the same rule. I've got to times that by 40. And when I times that by 40, I got, let's see, it's 14.142. So that's 2 of them done. Now obviously I've got 2 more intervals to do. So now the third probability, if I do it, is the integral Again, it said pi by 2 at the bottom, and it said 3 pi by 4 at the top. I'll just write that again. Of course, it was a half sine x. And again, it's no surprise. It's the same answer. We're doing the same integration every time, so there's the same answer every time. It's just got different limits. And each answer kind of repeats itself because you're repeating the same limits on each one. So this time I've got, when I did this, I got root 2 over 4 again. It came up again. But when I put the pi by 2 in, I got 0. So you can see it's root 2 over 4, which is still 0.3536. And when I times it by 40, I still get 5.8586. Oh no, it's just me being silly. That it was 14 point. That was the next one, 14.142. The next one is the probability. Now again, I'm going to end up with minus a half cos x when I do my integration. But now it's between 3 pi by 4 and pi. And when you chuck those numbers in, I got a half, because obviously cos of pi now is 1. So cos of pi is minus 1. So minus a half times minus pi is plus a half. That's right. And then I have to minus root 2 over 4. I keep on getting root 2 over 4s all over the place. And that is 2 minus root 2 over 4, which again is 0.1464. And if I times that by 40, I get 5.856 again. So just remind us of what we've got to do. We've got to calculate this chi-squared figure. Now I could work it all out, or I could just chuck it in my calculator and let it do the work. Chi-squared equals that. And so I want you to chuck this in. Like I said, you could put it into the GOF test. So you put it into list 1. List 1 should read the 4 numbers they gave me: 7, 12, 11, 10. 7, 12, 11, 10. And then list 2 should be the 4 numbers I got. The 4 numbers I got were 5.856, 14.142, 14.142, and then 5.856 again. So put those in and see what you get for chi-squared. Interestingly, I got chi-squared equal, I'm trying to remember what it was now. I did this sum in advance, so I should just make sure. I got 4.17. So bear in mind what we're saying. Basically we're saying H0 is that the model is supported by the data, the theory, something like that, by the observed data. And H1 is it is not. And I suppose the model is not supported. I'm not going to spend too long writing that. So we have got to look up the chi-square value in the critical value table. So degrees of freedom, we've got 4 categories. So degrees of freedom is 3. It said 10% level. Now you look please at the 0.9 line and look down it for 3 degrees of freedom. So on my table, on the 0.9, I've got 6.251. So a critical value of 6.251. Now you'll notice my value, 4.17, is less than 6.251. So we do not reject H0. Basically, when we're under, we do not have enough evidence that the model is wrong. So therefore we have to conclude that there's not enough evidence to reject it. It doesn't mean it's right, but we just haven't got enough evidence. And we would then say insufficient evidence or something like that. We do not, I didn't write it, but you definitely want to write insufficient evidence to conclude. So I'm running out of time, so I won't write it, but you would want to make sure you write down what that tells you in looking back at the PDF originally. Now there's another example we'll do in class, but then we'll do exercise 7i. And it's quite good that we've got another example to do in class. As you can see, this is quite complicated, and we managed to do one in 15 minutes, so that tells you it's a big old question, but one that we'll speed up on, and it won't take us 15 minutes in the exam, I'm sure. So okay, I hope that's okay, and we'll finish this in class.